Here we can see just the last one. Yeah. Yes. So here we can see how this advanced packaging, in the present day advanced packaging, has evolved from the basic packaging which used to happen in the 70s and 80s. So the earlier, so the first such processor from Motorola, which came in 1970s, 4004, and then Intel also came up with this another version of 4004. Then 8085 came, 8086 came, and then the Pentium chipset started. So these things have started from those era, and now we have reached a point in which the palm tops are more powerful and have much more bandwidth and memory than these older generation bigger computers. And this one of the main reasons that we have achieved this is because of the advanced packaging technology of today. And it is apart from the various advances in the material sciences, various advances in the fabrication technology. Like earlier, it used to be a normal photolithography. Now it is the extreme UV photolithography. So the kind of imprints which we are able to do for the fabrication is of a very high quality. That is why we have come from 350 micron technology node to 3 or 7 nanometer technology node. So this is on the side of the technology. But apart from it, we have also achieved commendable success on packaging technology. Here, the participants should note that in the recent times, Government of India's main focus is to introduce companies in India which are into packaging to start with this ecosystem, which are involved in the advanced packaging technologies. These are the companies like Micron is starting its packaging industry. It is called OSAT. So packaging industry is coming up in India through Micron or through Tata Electronics. These are the gateways of the major ecosystem of the semiconductor industry. So when Taiwan was establishing its semiconductor industry in the early 80s, the first thing it started to build was the packaging industry. That so there are two reasons. One is that the job demand is tremendous, because here the manual intervention is required in fabrication and all such things. Most of the and masking things, making of masks, making of doing the photolithography. These are mainly automated processes. So human intervention is less, and with the kind of AI which we are which intervention and adaptation of AI in modern industry we are seeing, the automation, the kind of automation we are seeing in modern industry, human requirement or the kind of employment generation which generally happens in modern industry will not be the case for the core semiconductor industry, so to say. So there will not be much demand in the factory production or the factory setup of photolithography, but there will be huge requirement of manpower when it will come to advanced packaging, because packaging not only requires human intervention, but it also requires a lot of different testing parameters. So when you go for a very advanced packaging, so before you finalize the packaging, when before you do the final packaging, you have to be very sure that your individual components, individual ICs are in their best shape and are giving the best quality outputs. Then only you proceed for any kind of final assembly. So here manpower requirement will be huge. And if you have seen the reports in the recent times, that Micron is asking for for skilled manpower, or in the recent times we have seen Tata Electronics sending its manpower to Taiwan to learn the skills of the trade. Essentially they are going to learn the tricks and the skills of packaging. That is why this packaging thing is so important, and we are trying our utmost focus to give this a proper platform. So when Madhukar ji was showcasing the entire bouquet of of instruments, it was very important to understand that those were the testing instruments that are used in some stage of testing the ICs and making the test beds. Once that is done, only then the final packaging is takes place. This particular thing, every individual and every participant who is eager to make his career in this particular field should understand that you must be having a very sound understanding of not only electronics and ICs, IC manufacturing, but also you should be having a very fine understanding of what kind of testing has to be done, what kind of testing should be done, and how it is done. So a good understanding of the testing test beds and test equipments are required. Now coming back to the evolution of advanced packaging, as you can see, we have gone from wire bonding. So a normal wire bonding means that the your dice, that is the single wafer based IC, is clubbed with the pads, the outside world pads, through normal copper wires. So that was what was the case in the early 80s, late 80s and the early 90s. Then we have gone for the flip chip bonding. Flip chip bonding, FC bonding, is that you just flip your active part of your IC wafer die, and then you bond it on a through a bump. That is, there is no wire bonding. Why it is required? So when we go for a very high speed interconnects or very high speed some kind of a processor, so the kind of an RC delay. So RC delay is the Elmore delay, which everybody must be knowing. So when signal travels on a copper circuit or a copper wire, so there is always an RC element in so resistor and capacitive element embedded in any kind of a interconnect. So that the charging and discharging of those RC elements, which takes the form of some kind of a delay. So that happens. So to remove or to minimize that kind of a delay, we have gone from wire bonding to flip chip bonding. So after flip chip bonding, again we have gone to 2.5D. So 2.5D is a industry name which happened between the flip chip stage and the 3D modern 3D stack stage. So in 2.5D, it is a mix of flip chip and 3D stacking. So now we have come to a 3D stacking in which multiple layers are stacked one above each other and connected through TSVs, through silicon wires, and those numbers can be huge. In fact, can be more than 15 or 20 in the vertical stacks. Now we have come to the level of a chiplet. Chiplet is, you can think of chiplet as the small bricks which are used to manufacture a wall. So suppose your final product is a wall, but you are not making a wall out of a one single element of bricks, but multiple smaller bricks. So chiplets are similar to those bricks. They are the smallest ICs which can be produced, and then they are brought together and joined in particular fashion, either in 3D way or through interposer, and then they are made out to be a system. This is the latest technology. There are various advantages, but there are multiple challenges also. One of the challenge is obviously when you is to manage such kind of handling multiple different elements of chips in terms of latency, in terms of power, in terms of synchronization. So multiple challenges arise, but still these days the complex systems are being manufactured in a chiplet form. So people who may be aware, earlier there used to be a wave of called system on a chips, SoC. So SoC used to be a kind of a system in which one system used to be manufactured in a proper integrated fashion. So suppose a computer CPU had to be manufactured. So the entire fabrication used to be done in a one go process. So that fabrication would entail fabrication of memory, of the ALU, of the buses. Everything used to happen at the same time on the same wafer. Now with chiplets, What we do is that we manufacture memory separately. In fact, various stages of memory can also be manufactured separately, like read and write circuitry can be manufactured differently. That will be one chiplet. Another, the storage part will be another chiplet. Then we will combine it together and we'll make it a final memory. So this is how the packaging are being done these days. This is also very important from the supply chain point of view, because some countries may be very good in the design of pure storage elements. So Taiwan, for example, may be very good in the manufacture of storage elements, storage part. But interconnects, maybe some other countries, suppose Netherlands or Japan, may be very good in designing of your interconnects. So what the basic business sense says is that you bring in the storage elements from Taiwan, you bring in your read writes circuitry from Japan, and then you do the integration. So this is how the chiplets work, and they fall in the category of comparative advantage. And this is very important from semiconductor industry point of view, because semiconductor industry still runs on a very thin margin, because not only because of the competition, but the kind of input or the kind of capital which is required is huge, and the market is still growing. So the semiconductor industry traditionally works on a margin of 8 to 10%. So even 1% or 2% of additional margin or advantage is of huge benefit. So these kind of things, chiplets and all, are not only important from technology point of view, but also from a business point of view, and that everybody should understand these issues very keenly and thoroughly, because in India we are trying to take advantages of these kind of tricks. Now, I have just seen, is chiplet solution effective for small system design? Absolutely, chiplet solution is fantastic for small system design. When you say small system design, I may think of something like a normal processor, or a reader, or something like a handheld device or something. But when you go for a GPU kind of an application, then chiplet is not that important, or now it's not that preferred a choice. But as far as we understand, there are some technologies, especially in South Korea, which are trying to have chiplet technologies even for the manufacture of GPUs. But we are not very sure of what kind of results we have got. But for smaller systems, like for example biometric reading system, so chiplet technologies are essentially used for all kind of biometric reading systems. So the display devices are kind of one part, then the reading part will be another, the storage part will be another, their wireless connectivity can be another. So there will be three or four kind of chiplets. We will come and integrate it. So this is how the in India, there is a phrase which government is trying to promote. It's called electronic system design and manufacturing. It is called ESDM industry. It is happening for the last 10, 12 years, but in the recent times, we have seen that major impetus from the government is happening. Lot many companies have shown interest. Government is also trying to uh, uh, give every kind of subsidy and incentives in terms of finance, in terms of other export incentives and all, so that final electronic manufacturing happens in India. That manufacturing activity at this point of time and in the near future is solely dependent on the chiplet technologies. We will be till whatever technologies we are very confident of, or we are self-reliant, those kind of technologies we will be manufacturing. But for the rest of the things, we will be still importing, but we will still be doing final integration. One of the final example is the kind of Apple phones which are being manufactured here in India at this point of time. You can think of this as one of the major success stories also of India, and and the successful implementation of government policies. So we still import, we don't manufacture much of the things, but we import lot of things, the components which goes into the Apple computers and Apple iPads. But we do this kind of thing here in India, the integration, and that is a representation of a chiplet technologies.